A lot of code today. So I put something in the chat saying that if you hear me type yes, I had exactly one college type yes, that was Jntuk Kakinada, and no one else typed no. That means they are not sure whether they are able to hear me or they are not able. They are not sure that they cannot hear. There are only two options, yes and no, right? So if others are able to hear me, just type yes. Okay. So Aditya muted themselves. Aditya College, if you can hear me, you can type yes there. Gits, are you on audio? Yeah. If you can hear me, type yes. ASET, the same thing. Okay, JNTV saying good morning to everyone. Good morning, JNTV, and I'm assuming you are able to hear me. If so, please type yes. Great. Do we have, I don't see videos of anyone other than JNTU Kakinada. You can turn on your videos too, rest of the colleges. That way I know students are there, not there. Okay, so I like this quote. I don't know why I picked this up. I think my kids always hear me about working hard and achieving success, right? Keep plugging away, all kinds of preaching, I guess. I like this quote because they always try to encourage people, saying that don't worry about failure, it is a step towards eventual success, right? That always reminds me saying that a stupid young man can become a grand and a stupid old man, You cannot become, just because of age, you cannot become like all of a sudden a very wise man, right? So there is some effort involved in going from ignorance to somewhat knowledgeable. Similar thing here, right? Yeah, mistake is the first step, all right, but as we say, the real fact is correction of the mistake is the first step. If you keep making the same mistake, right, one would never succeed. So in that sense, I like this quote. Okay, it's been a while since Chakravarti Garu gave, or other faculty members can put some nice quotes too in the chat for students to enjoy them. What are we doing today? Couple of things. When I do review, we are adding some additional insights to along the way, okay? Not just rehashing what we learned. Along the way, you look at it from a slightly different perspective. Then we'll get to come to an exercise, actually. I looked at the exercise. Actually, it might take the full class or half the class or 15 minutes. I don't know. Quite honestly, I don't know how much time the exercise would take. And originally, I thought of starting off the class with the exercise because typically some institutions come late. I thought at least others can get going on the exercise. But I changed my mind. I said, let me do a quick review of threaded binary tree. Then we do the exercise. And if time permits, we'll get into code samples directly after the exercise. Or maybe I'll do the code samples, make you do the exercise. We'll figure it out, okay? Loaded class. So let's pay attention, and then when I ask questions, and when I ask you to put something in the chat, please do so. How to type, whatever reasons are, right? Okay. So quick review. For those of you who have missed, they come in late, they just missed this, but we'll post it in the community. So that is what we did last class also, right? We defined what a threaded binary tree is. And it's nothing but a binary tree. And then what do? We deal with all these nulls that are there at the end, at the leaf nodes, right? Because ultimately when you implement a binary tree, it has a certain structure. Every node has a structure. Data, left and right, right? Left child, right child. So when you reach to the leaf level, those left child, right child are null values. So we are saying, null values are not so great. So we'll make use of those null values. Instead, we'll make them point to something. That's what a threaded tree is. So the first point says here, all the left child pointers that would normally be null point to the in-order predecessor of the node. Note the keyword here, in-order predecessor. Predecessor is what comes before, right? And then you have the right pointers, okay? And they point to the post-order successor. I mean, in-order successor. What am I thinking? In-order successor. Okay, so left pointer points to the in-order predecessor, right pointer points to the in-order successor. That's rule number one. Instead of calling them pointers, we call them threads. Okay, as opposed to a regular link. Regular link is like you have left subtree, right subtree, and so on. Those are regular links. To distinguish from regular links, where we are basically replacing the null pointers with these things which replace the null pointers are called threads. Okay. The question then is, why do we need thread binary trees? What is the big deal, right? The big deal is this should tell you the two most important advantages. Number one, typically binary trees have a loss of wasted space, right? Because each leaf node has two null pointers. Null means it's not doing anything, right? So what some smart Alec has done is, I shouldn't say smart Alec, some smart professor, when way back in the 60s, famous Stanford professor Donald Knuth asked the question, hey, a lot of space is getting wasted and we don't know what to do with that. What could be an ideal solution? So some other professor came up with the solution saying, hey, I'm going to replace the null pointers with some concrete data. Okay. Now, in the process of doing that, the birth of threaded binary trees happens, and it also enables people to do the tree traversal faster. Somebody join, mute yourself please. I'm getting static. Okay, I'm muting ASET. I'm muting Chaitanya. Good morning, Chaitanya. Okay. I'm muting SVCW. Good morning, SVCW. For those of you who just joined, we are just doing a quick review of the threaded binary tree. I just covered one slide. Let me go back there. Okay. What a threaded binary tree is, and then so that was a quote. Okay. So why do we need them? Because we want to get rid of that wasted space, the null space. And then in the process of doing that, we also make the traversal faster. Because once you have the concept of threads, you no longer need to build a stack or recursion. As you know, when you have recursion, you need a stack, activation stack, right? So, and to build all of those things and to traverse would take longer. So by using the concept of threads, we are killing two birds at the same time. Now, when you have thread binary trees, there are two distinct classes. One is single threaded and the other one is double threaded. Okay. So that's the definition again. Each node in single threaded Each node is threaded towards either the in-order predecessor or successor, okay, depending on whether it's a left or right. Okay. So as you can see in that statement there, all the right null pointers will point to in-order successor, or all left null pointers will point to in-order predecessor. Now, if you can also declare something as double threaded, where each node is threaded towards both in-order predecessor and successor. So you have two threads, both point to predecessor and successor respectively. So here is a quick example. One on the left shows you single threaded, one on the right shows you double threaded. So when you have a tree, remember the tree operations, right? We covered a lot of tree operations. Here is one example of how to insert a node in a threaded tree. What are the components of a tree to begin with? If you look at on the right side, okay, you always have every node has data, left and right. We know that from binary trees, right? You have data, you have a left which points to left subtree, and then right it points to right subtree. Now notice one thing here, saying that right threaded equal to false. Within that node structure called right thread equal to false. So we'll see why we have that condition. As we go along, as we look at the code, we'll see why it makes perfect sense to define a new variable called right threaded and initialize it to false. Okay. On the left, you see some C++ code. Because the moment you see class, it's either C++ or Java, right? So you have data corresponding to the three on the top. There you have data, you have left and right. Where are left and right pointing to? They're pointing to other nodes, right? That's the reason why the type, if you look at it, it says node left, because it's pointing to objects of type node. Okay. And then is right threaded equal to false, it has two values, either false or true. So false and true means it should be a Boolean. So that's why you see Boolean right thread. Okay. Here's some illustration there. How do we insert a node there? Okay. So here is a little bit of an algorithm. And I am not going to explaining this thing in detail and writing stuff, but it's there for you to review later. So you start at the root. That's why take current equal to root. Okay. So you are going to, since it's a binary tree, we already know that whatever key value that we are looking for, we compare it with the root's data. That's why you see start from the current and compare the root, the data that is there in the root node with n, because n is our object of interest. Okay. We keep track of parent node while moving left or right. Ultimately, when you travel the tree, all of those nodes, intermediate nodes, are either parent node or not, right? So we have to keep track of that. Depending on whether the current data is greater than what we find in the node, you either move to the left or to the right. Okay. In the case of current data greater than n, meaning n is what our key value, then we go to the left of the root. Okay. Now when you go to the left of the root, you can see some instructions there. The current equal to null. Remember, each node has pointers. If current equal to null, that means we have found the place where we want to insert the new node. Okay. If current is not equal to null, that means there are more values. So you continue with your comparison, and at some point of time, when the value that you're seeking is less than the current, then you add that new node. Okay. That's what this slide is saying here. So this is a very legitimate question. Given a binary tree, how would you go about inserting a node into a binary tree? Sorted binary tree, obviously. Okay. So here is an example of how to insert a node in a threaded T. So you have 20, 10, and 25. If you apply the algorithm, 5 is less than 20. So you go to the left subtree. Right? Compare the value with n. Then 5 is less than 10. You go to the left subtree. Now, if you go to the left subtree, you see that 10, the pointer is pointing to null because there is nothing there. Since the pointer is pointing to null, then you know that you have reached the end of that subtree. So you are going to insert that element 5 there. Now, the moment you insert element, you change that value of the boolean to true because you started with false. So you go in that loop till that gets inserted. Okay. It's kind of easy to explain using a slide deck, but once you start writing code in the lab, I'm sure you'll make some silly mistakes. Okay. Now, similarly, just like if current data is smaller than n, because n is what we're trying to insert, that means we should go to the right of the subtree, right of the root. The reason why we are doing left and then right of the root is that tree is ordered. Okay. Ordered means there's an increasing order, some order, whatever that order is. Okay. So we are trying to insert 15 into a binary tree, and then you can see the pictorial there based on the algorithm that we talked about. So we know how to insert. Now, how do we traverse? Okay. So in the case of threaded binary tree, there is no need for any recursion or any stack because we already have the threads which would guide us. Okay. So the way the algorithm works is you go to the leftmost node and start traversing the tree using right pointer. And then whenever you have that right thread equal to false, right, then you go back again to the leftmost node in the right subtree. Okay. You don't need to memorize that. This is just to give you an idea, because ultimately you learn this by coding. So you can see here how traversal of a threaded tree, the author has marked the arrows there. How you went about traversing a threaded tree. Okay. So apply the principles for the when you visit a current node, whether the value that you're seeking is greater than or less than. Okay. I'll let you convince yourself how this works. Questions, comments? If you're silent, I just assume that you either know everything or you're totally lost. We need some interaction. Okay? Otherwise, it's very easy for me to finish the lecture in 30 minutes and say done. Exercise. What is it that I want you to do? Faculty members, please coordinate this because this is an intense exercise, okay? Give the definition there for binary tree one more time. Okay? I want you guys to do it in groups of 2 or 3, notebooks out, pencils out, heads down, right? And start working. First question, draw a binary tree. It should have nodes A through H. And it should be drawn in such a way the in-order traversal results in A, B, C, D, E, F, G, H. Okay. Now step number 2. As you write a representation of these alphabets corresponding to the in-order traversal. Okay. So we talked about how to represent a tree as an array. You have to recall what is the concept that we discussed there, right? There's a concept of indexing, the proper indexing, and things like that. Thank you, SVCW faculty member, going around and making your students do. I appreciate that. I'm excited. Okay. So after you do first two steps, then you have to show a threaded binary tree for the above. And I gave you the rules. Okay. And then I'm saying show those things in both the tree as well as array. So how do you show it, you might ask, right? Let me put it in small one, right? Tree, you know how to do it, right? You draw an arrow, right? What if I say like, let me insert something here. So if I do like an array, how do we draw an array now? How do we draw an array? There should be a table, right? Insert, table. I think this is one array, right? Okay, that's an array. So let's say I put some numbers here. 1, 2, 3, 4. Believe me, I am typing. Oh, I typed everything in one place. I didn't want to do that. Let me select the. Let's say I say 1 here. I say 2 here. I say 3 here. I say 4 here. Okay. So as you are doing the thing, I want you to show an array like that with the numbers, right? And somewhere I said show it, right? Like for example, you have a left arrow going from, where are the arrows here? I have some lines here, right, somewhere. I think I can use one of these lines here. Where are the lines here? How come I can't see my lines? After I got Windows 10, I don't know where things are. Left arrow, left arrow, left arrow. Like I can take a left, going left here like that, right? You can draw free writing like that. Let me, right? So 4 should point to 2. So there's a way of using not straight line like this, but a curved line, right? I chose the wrong line. I can choose something like that, right? So, like that. Okay? So going left from 4 towards 3, 3 to 2 and so on. And on the top, you can draw the right lines. Okay? I'm screwing up here in terms of doing it properly. Let me delete that. You are better drawing the lines. Okay? So that's what I'm saying. So left and right, both. Because you have a left child, right child, right? So if you show all the left childs at the bottom, show the top children on the top, and vice versa. Okay. Let me go back there to. After you do this, there's one more exercise and more exercises, right? So if you are, after you're done with that, then we come to the next one. Okay? And then after you're done with that one, we do other things. Okay? Okay, I'll leave this on. How about 15 minutes? 15 minutes is the limit. If you're done sooner, if about 2 or 3 teams are done sooner, you can put the word called completed. And then you can type in your solution there. If I get about 2 or 3 groups done from different colleges, then we'll move on. Okay? Ready, set, go. 15 minutes from now, we'll start. And if you turn on your videos, I can watch the wonderful students doing all this good stuff. Pragati, you can give me some feedback in the chat. The data, it has left and right. And left and right are pointers to the same node, right? Because every single node has the same representation. So we have a left pointer, right pointer. And every node has those three, so I'm representing that. Now this is only declaration, but it is not allocation of memory, remember? So how do you get the memory allocation? So you have a function, I already gave you new node. So what does the new node return? Whatever the new node has been allocated, it is to return a pointer to that, right? So that's why the return pointer is node star, meaning pointer to a node structure. And you are creating a new node. Every node has a data value, right? If you look at the struct, so you need to pass the data value. That is the key. Okay. Now, how do you do that? C function by calling new node. You could do that. You could, if some of you could have written as malloc, right? You can either do malloc or new. There are some differences between new and malloc. Just read it up, then you will know the differences. These days, generally, people use new. Okay. And then you are saving it. When it's allocated, you need to save it somewhere. That's why you have temp.left and temp.right, because you just created a node. The node left child and right child, there is nothing, because the very first node. That's why you make them null. And the key value, you get the key, and then you're returning temp. Okay, when you return temp, where is it going? So if you want to test these two pieces of code, what do you need to write? You need to write what is known as a driver function, right? So what is the driver function? You can write something like main, right? You know, every C programming has a main. In main, you declare, and then from there, from main, you would be calling this function, correct? The struct could be within the main. And then when you call new node function, whatever it's returning, in the calling function main, you would have a variable that takes the address of this into that. Okay? Just making you learn some of these things. That's all I'm doing, or making you review some of these things. Okay? Let's look at the code a little bit, not much. At least today, not much. We'll see. So I'm showing a couple of examples here. Jntuk Kakinada's answer that you put, maybe you applied this one. So typically, when you're given an array and you want to construct a binary tree, the way it is constructed, there are certain rules. Okay, mapping the array to the binary tree, there are certain rules. Okay. So with respect to parent, we are saying that parent of a node at index lies at n-1 over 2, except the root node. So if the parent is at 5, n equal to 5, 5 minus 1 over 2. Okay. So that will be the parent of the node that stays at that index. Okay. So left child of a node at index n lies at 2 times n plus 1, 2n plus 1 as we say. Right child would be 2n plus 2. Now this is, I think you are taking the index starting at 1. Somebody could verify. If we're starting at 0, I think this will be just 2n. You can check it out. Similarly, every node at a given level has a left sibling and a right sibling. So if you're reading from array, take it from n minus 1 and n plus 1. Okay. Kind of covered this in one of the lectures before, in a slightly different way. Okay, let's look at some code here. Give me a second, I'm trying to adjust my screens properly. So array to binary tree, right? So tree has nodes, so that's why we declared these three, remember? Here and go back to struct. You have left side, right side, and then the data. And type def means it acts as a synonym, right? We are saying type def structure node as node, and then meaning you're inserting a node into the tree, right? I'll come back to the details here. And then the other one is you're traversing the tree. Traverse the tree in order, okay? And then you have the main program, okay? So what does the main program have? We have since you already defined the node, we are saying, hey, my tree is a pointer, node pointer, initially null. Null means there is no tree, correct? We just started. That's why you declare the variable tree there. It's a pointer. It is null. And then it is hard-coded here. What are we doing here? We declare a character array. You know, from C, I don't need to specify the dimensions of the array. I can put open things here. But the rule says you have to specify, you have to initialize this at the same time. If you don't initialize it, the compiler would give you an error. If you keep this open without any dimensionality function specified. So by saying that, okay, it's a character array, so you're inputting characters. Remember we said when we use array for tree representation, it's good to have a big array. When you apply those rules, if you go back here to the previous page, see the rules here? Where the parent is for a given node, where the left child is, the array size becomes humongous. So here you can see he has given that. Our main elements of the array are A, B, C, D, E, F, G somewhere, right? Rest of the spaces are null. Okay. Now what are you saying? Tree equal to, because you're building the tree, remember? You're saying insert C, comma O. It's not O, it's 0. So you're saying, hey, insert the elements of the character array beginning at position 0. So after you insert the tree, then you do an in-order traversal of the tree. So here, main is pretty straightforward to understand, right? We declared a tree. Tree should have, what is the data structure of the tree? The data structure or the data type of the tree is that of node. So every node would then contain whatever this node structure is on the top left. We have all those three, left, right, and data. Okay. So now let's go to insert function. So in insert function, NS. Okay. So now, since you have to insert, we do know that we are going to get a tree node initialized to null. Now this tree here, pointer tree, null, and this one, they are in different functions. Notice that. Now if C of n not equal to 0, meaning null, see this null, all these null characters. So n is 0 to begin with. So is it null? C of 0, no, it has A. Then you come into this loop here. Okay. Now we need to get the node allocated. Allocated means you have to get it from memory. So what do? You do a malloc. You could have done new also. Okay. If you do new node, you don't need to specify the size of. New already has that code built into it. Traditionally, malloc did not have that. That is the reason why you say malloc. Malloc means memory allocation. M stands for memory. And how much memory you need to allocate, you're telling the compiler it should be the size of node. The node has these three elements. So the system knows how much to allocate memory. Memory is nothing but address. And then our variable is tree here. So now tree is going to point to that address because that's where the node is. The first node, that would be your root. Okay. So now we say tree.left, insert C, comma, in that character, 2 star n plus 1, data get data, CFN, okay, in this case A, right gets C, comma, 2 star n plus 2. Now where did you get 2 star n plus 1, 2 star n plus 2? If you look at the previous slide, so you said, right? Left child of a node at index n lies at 2 star n plus 1. Right child of a node at index n lies at 2 star n plus 2. So once you are here, now at the end here, if you see how this loop is going, then he said after you do this one, then you go tree.right. So once you're done with the left, because remember you have to keep building the left tree. So you are going to be in this loop here. Okay. The question, a good, interesting question would be when I give a piece of code in an exam like this, I can ask you, hey, for this data, how many times is tree.left equal to insert C 2 star n plus 1 would execute? How many times that statement would be executed for this data? And same thing for this tree.right.insert C, comma 2 star n plus 2. Okay, let me pause here. Questions, comments? Are you half dead or having fun? Unless you execute these things in the lab, you would not appreciate, right? So these are almost working pieces of code. Okay. So what are we doing here now? Convert binary tree. So I showed you how to map array to binary tree. Now we are looking at converting a binary tree. In the exercise, I made you build all the binary tree and all that for you to get practice and gain some insights, right? And then that way, when I teach this one, you will appreciate that. So the goal that we have here is to convert a binary tree to a threaded binary tree. Okay. So how do we do that is the question, right? Let's look at it. I think I have a whole bunch of slides here to explain this one. I won't go through each and every line. I want you to go through that and make sure you understand, right? So you have the node, okay, this on the left side, okay. So what is the difference between the node that we have seen before and the node that you see here? Let's look at it if there's any difference, right? Integer key is nothing but the data value. We have that earlier. We need left pointer pointing to node, right pointer pointing to node. We have that too. Okay. So I made you do the exercise. You didn't come to that point number 3 yet. Once you finish point number 3, you would appreciate these lines of codes, where we are saying we'll introduce a variable called in order successor, okay, and then a Boolean value is threaded. Remember, we are basically replacing the null values with a thread. Now you have to keep track of it, right? Whether it's a thread or not. Remember, we said once you do threaded binary trees, you have regular links to left subtree, right subtree. But to distinguish replacement of null values with a thread, you need to have some mechanism, right? The mechanism is simple. Declare a Boolean called is it threaded? Is that value threaded? Is that cell threaded? If it is, then it's a thread. If it is not, it's not a thread. Okay. Now, here on the right, I said it's a function to put the nodes in order into a queue. I mean, queue is almost like array, right? Almost. Obviously, there are differences. Okay, don't jump on me. You can index into an array, whereas in queue it is first come, first served. But what is he doing there? So he's saying if the root is null, return, meaning there is no node. But if there is a node, root.left returns true. Okay. So when it returns true, you're saying, hey, you know what? I'm going to put, there's a function called populate queue, right? That is this one. You are going to call root.left and queue. Okay. So I know I'm explaining what you may not understand. You need to take some test data and go through line by line. That is the next step. I taught you that technique too. So basically what he's doing is, as he is reading these values, he's pushing them into some kind of a FIFO structure called queue. Okay. Now, why is he doing that? Okay, let's look at it in the next slide. So next slide shows once you put something in the queue, from there you have to put it into a tree. Okay, so he took some values that came, he put it, queue is almost like an array, and from there he's going to build the tree properly. So in order to do that, we need to traverse the queue. So there's a bunch of code here which shows you how to traverse the queue. Okay, I'll come back to it later, but there's a bunch of code here. Okay. If you go to the next slide here, I'm seeing where let me go to one more slide there, because I wanted to start with main. If you look at the main function here, the tree that you're trying to build is that 1, 2, 3, 4, 5, 6, 7. Okay. Remember, most of the main functions are called what? Driver programs, right? To test our code. So what are we doing here? We are going to get a new node first, because we have to build a tree. Okay. Now once you get new node, what is the data value for the new node? 1. So where is the new node function? New node function is right here. What does it do? I made you do it in the exercise, right? It's going to get a temporary node. You're going to initialize temp left, temp right equal to null. The value is 1. We know that. Okay. Temp.key get key value. That is 1. And then you're returning. The reason why you're returning temp is in the caller function here, you can see that is a root. So declare a variable root of type node. Okay. Root.left is what, based on the picture that we gave. Again, remember it's hard coded here for simplicity. The root.left is new node 2, root.right is new node 3. So then you say left of left, because for 2 also is the left, right? That is 4. Left of right is 5. Now we come to right. Right of left is 6. And right of right is 7. Now this is where you have the structure. Now the question asks for creating a threaded root. Okay. That's what we are doing here, right? To create a threaded root, remember the definition of the threaded root. Okay. After you do that, the proof is in the pudding. That is the reason why he's saying, let me do an in-order traversal of the created thread. Why I keep going back. So when you do that, so he's then going to show how, when you do in-order traversal, what is the order in which this tree gets printed, right? Sorry, I keep jumping there. Okay. Okay, so there is code there for you. Okay. So it's not easy it's not a one-layer function, right? There are multiple recursive calls and things like that. You have to get used to that. It's pretty much a working piece of code, at least on a piece of paper. You can take some test data. What I suggest is, instead of me just going through these things in an abstract way, take some test data. Okay? That's the reason why I made you do that exercise. If you finish those exercises, those 3 things or the 5 things that I put there, you come back to this code. Now take those things as test data and go through this code. You'll understand every line of it. Okay. I was going to do some binary search trees again, but I'll stop there for today. So I said I'll come back and give it to you, give the time to you to do the. So just to recap, I covered two things. One is converting binary to threaded. The other one is just like building a tree itself. How do you build a tree using an array? Okay. So go back to your thing here. Try to finish this one. And after you finish that one, I'm going to post that code in the community right now while you're doing it. Then you go back and revisit the code and do a dry run of that code using the data that you are getting here. Okay? Any questions, comments? You have a solid 20 minutes to finish this exercise today. Okay? I will go on mute and then I'll try to upload this slide deck for you while you're doing this. Okay? Put your questions in the chat. Okay? While you're doing it, I'm going to take this slide deck and post it.